Hello, class. Today's discussion is going to focus on these two words here. We have what's called a substitution reaction and an elimination reaction. Two different, what we call mechanisms. And mechanisms are how the reaction occurs. And you will see very shortly that mechanisms are going to be key for your success in organic chemistry. If you can learn the mechanisms, then you can understand the reactions. So as we go through the course, I'm going to teach you 10 basic elementary steps. And these 10 basic elementary steps are the 10 different types of mechanisms that if you understand those 10 elementary steps, which are basically just mechanisms, then you will be able to understand 90% of all the reactions that you'll ever encounter. Because how many reactions are there? There are hundreds of thousands, maybe even millions of reactions. I don't know for sure. All I know is there are a lot of them. And it is not possible to memorize all the reactions. But what is more possible is learning and knowing those 10 elementary steps. And if you know those 10 elementary steps, you don't have to memorize as much. So now I'm going to get off my soapbox, but that's key. Once you need to learn mechanisms, it will really help you. So what we're going to learn here is substitution reactions and elimination reactions with alkyl halides. So for example, we could have carbon here, an alkyl halide. Let's put a chlorine, and then we have some R groups here. Now these R groups could be hydrogens, they could be alkyl groups. Doesn't really matter. We just have an alkyl halide. Now this is this halogen right here, which could be represented by X because we want to incorporate all alkyl halides, is attached to what type of carbon? Okay, that is a sp3 hybridized carbon. In contrast, if you look at something like this, you see that this carbon that the halogen is directly attached to is sp2 hybridized. So we are not going to talk about any examples where the halogen is attached to an sp2 hybridized carbon. We will talk about that in chapters way down the road. We want to focus on this type of alkyl halide. And so this, you have to understand, can you see the difference? How this is sp3 and that is sp2. If you don't, then it's a good idea to figure out the hybridization states. Now, in substitution and elimination reactions, we have different components here. Okay? They all have different names. So let's say if we look at an alkyl halide. And when we take a look at this alkyl halide, we could treat that alkyl halide with a nucleophile. I'm going to represent that nucleophile with a negative charge. What's going to happen here? When you look at the overall process, what has happened? We have taken this halogen right here and substituted it with the nucleophile. So this is called a substitution reaction, when we are substituting the alkyl halide for a nucleophile. A nucleophile if you look at the word, okay, it's composed of two parts, nucleo and then phile. What that's saying is a nucleophile, represented by Nu, is nucleus loving. It loves to attack the nucleus. So what is going to happen here mechanistically, let's clear off some space here. Is in a nucleophile, we can have it, the mechanism looks like this. So we're going to take the nucleophile, and we're going to take the lone pair. And that lone pair is going to come and attack the carbon that is directly attached to the halogen. And when that occurs, what's happening here? If I stop with that one orange arrow, what have I done? I formed that bond. That's what the orange arrow is showing. But look at here. How many hydrogens were here already? There were 2 hydrogens. So now what do we have? We have a Texas carbon, and that's not possible, right? Not possible. So mechanistically, what's going to happen is as the nucleophile comes in and attacks the carbon that's directly attached to the halogen, the carbon-halogen bond breaks. And so we already have the 3 lone pairs on the halogen, but then it's going to break and dump both the electrons onto the halogen. So now what we have, the nucleophile attack to that carbon, and if we want to number them, 1, 2, 3, 1, 2, 3, the nucleophile attacked carbon 3, you see it's attached to carbon 3, and then we have the halogen came off, so now that halogen is negatively charged. And this is what a mechanism is all about. It's showing, so this is just an overall showing us the transformation, and this is called a substitution reaction. Yeah, the halogen is replaced with the nucleophile. Great. How does that transformation occur? That's where we come up here to the mechanism. And if you can learn this mechanism and all the others that I'm going to show you, organic chemistry will be easier, I promise you. You cannot memorize your way through this course. Got to understand the principles. And here's the mechanism here. And this mechanism has a very special name. It is called a S subscript capital N2, an SN2. We will talk about what that means a little bit later. I'm just introducing this at this point. So this is a SN2 mechanism. When you have an alkyl halide and the nucleophile attacks the alkyl halide in this manner. Now we have eliminations. Well, let's leave this up here so we can compare and contrast. There. So I'll erase the top. Now, let's take another alkyl halide. Looks like that. And let's treat it with a generic base represented by the letter B for base. And when we have a base treated with an alkyl halide like this, what we're going to generate is a compound that looks like this. We generate what functional group is that? That's an alkene. And then we also generated a BH right there, plus the halogen right there. All right. So if we look at the lone pairs, like so, like that. Okay. So what has happened? Well, do you see how the base did not substitute the X? See how the base isn't even attached to the molecule of interest? This is the molecule of interest. The base isn't attached to it. But what has happened? We've eliminated the X off of the molecule, and we've eliminated a hydrogen. Do you see at this carbon right here, if we want to number them? So 1, 2, 3, 1, 2, 3. Carbon 3 on this side, on the alkyl halide, we have what? 3 hydrogens on this carbon. Come over here. How many hydrogens do we have on carbon 3? Only 2. So what have we done? We have eliminated the halogen and one of the hydrogens. And so when you take an alkyl halide and treat it with the base, you get an elimination reaction, which gives you in this particular case, an alkene. You're going to form a double bond here. Now, mechanistically, how is this happening? And we'll just use this right here. Let's draw the mechanism here. How does this happen? Well, the base is going to come and abstract the proton. That carbon-hydrogen bond is going to break. Do you see what that carbon-hydrogen bond breaking? It dumps its electrons right here. So that pi bond right there is generated from the electrons that are found between the carbon and the hydrogen. But if I only have 2 orange arrows, then I have formed a Texas carbon. I also have to get the halogen to leave, like that. So the carbon-halogen bond breaks, dumping the electrons in that bond onto the halogen. As you can see here, now we have 4 lone pairs. And that is going to generate our alkene. Oftentimes, now this is the crazy thing, watch this. Oftentimes, the base and the nucleophile can be the same molecule. So for example, let's say I show you a base. Let's say the base is going to be hydroxide. Hydroxide can behave as a base, whereas it can also behave as a nucleophile. So what is the difference between, let's do it in subscript here. We're going to call this one a base, and this one's going to be our nucleophile. Okay. They're the same molecule, but the way they behave mechanistically is different. Because in the base, you see the mechanism arrows, right? The base comes and abstracts a proton and then kicks off the halogen by forming a double bond. That's what a base does. But a nucleophile is one where it comes in and does a substitution reaction. Let's draw in some lone pairs here so we can see the charge. So because hydroxide can behave as a base and behave as a nucleophile, when we do these reactions, we are going to get a mixture of products. We're going to get some of the substitution product, and we're going to get some of the elimination product. So this will be an example of an elimination product, and this would be an example of a substitution product. And so that makes organic synthesizing molecules a bit of a challenge, because what if you only want the substitution product or you only want the elimination product? It makes it a little difficult if there's going to be a mixture. But there are techniques that we are going to learn that helps us to persuade the reaction to go in one route to form the product that you desire, or the one that you want. Okay? So make sure you understand the difference between what a base does and a nucleophile. Bases abstract protons. Nucleophiles attack the carbon nucleus. So if we have a secondary alkyl halide like this, in order for us to do a substitution reaction, why do we need the alkyl halide? Why do we need that? And so we're going to take a look at that. Well, the halogen is what? More electronegative than the carbon, right? So if it's more electronegative, then it's going to pull electron density towards the halogen, right? And so what's the effect of that? Well, this carbon right here is going to be partially positive. And then when we take a look at the nucleophile, what is its charge state? It's negatively charged. So this negative charge is going to be attracted to this partial positive carbon. And that partial positive is generated because of the electron withdrawing ability of the halogen. And so when you have these two species in solution with one another, the nucleophile is attracted to this carbon because of its partial positive charge. And so we can see mechanistically it's going to be attracted to that carbon, and then the halogen is going to leave. And then we would get that product right there. So the reason why substitution reactions are occurring is because of the electron withdrawing ability of the halogen to make the carbon that the halogen is directly attached to electrophilic. It's electron poor. So in a lot of organic reactions, what we have going for us is we have an electron-rich species. And then we're going to have an electron poor. And so we have an electron poor carbon, electron-rich nucleophile, and it's just basic laws of attraction. Electron-rich is going to be attracted to electron-poor. And when we have an electron-poor site, we call that the electrophile. And when we have an electron-rich species, we can call it a nucleophile. Remember, nucleus-loving. What is an electrophile? Electron-loving. Electrophiles loves to accept electrons. Now, the reason why I said electron-rich species may be nucleophiles is because we just recently saw that hydroxide could act as a base as well. So, but I'm calling this a base, but it is still electron-rich. So electron-rich species can be a nucleophile or a base. But the point is that electron-rich species are attracted to electron-poor species, or the electrophile. Okay. Now the next reason, and another thing that we need to understand as to why we need a halogen is because we have a phrase. The halogen right here is a good leaving group. And I'm just going to abbreviate leaving group with LG. Halogens are good leaving groups. So you see in a substitution reaction, the halogen has to leave. And if you go back to your notes and look at the elimination reaction, the halogen also has to leave. Halogens are good leaving groups. If I contrast that, why does this reaction right here, let's put in a methyl group and treat it with a hydroxide. Why does this reaction not work? To give us this product. Why does that not work? And the reason why this does not work is because methyl groups are not good leaving groups. This mechanism arrow right here, or both these mechanism arrows, don't occur. It can't, because the methyl group will never leave. It's a horrible leaving group. But in contrast, halogens are really good leaving groups. Okay? So how do you know if a group on a molecule is a good leaving group? So here is the definition or the statement that will tell us if a leaving group is good or not. And it says, good leaving groups are the conjugate bases of strong acids. Okay, that's the answer. But now you have to translate what that sentence is trying to say. So to help you understand that, let's look at these two examples here. So we want to do a reaction with these. Is this iodine right here a good leaving group compared to this hydroxide group? Is that a good leaving group? So what we want to ultimately do is, can you do this reaction? Can you take a nucleophile and go in like this? Are both of these reactions possible, or only one of them? And if so, which one? Well, let's go back to this statement. So this is how you do it. You look at your leaving group, or your proposed leaving group, and you turn it into an acid. Okay? So if we take the iodine, we can turn that into hydroiodic acid just by adding that H. We will then add it to some water, okay? And we will see what happens. And now we are going back to acid-base chemistry here. So this is going to come in. The iodine's going to leave. You see how it's leaving off of the hydrogen right there? And what are we going to make? We're going to make our hydronium. There's the conjugate acid, and then there. Just like that. We go to the pKa table, and we figure out what's the pKa of the hydroiodic acid, and it has a pKa of a -11. All right. And hydronium is what? -1.7, I think? Let's see here. And then we contrast that, all right, with the other one. And what was the other leaving group? It was a hydroxide. So we will take that hydroxide and add a hydrogen to it, okay? And then put that into water and see what happens. Right? Okay, what's the pKa of water? About 16, 15 or 16. Right. So at equilibrium, what's going to be favored? Let's go back to this guy. Well, it's going to be favored to what? The side where there's the weakest acid. So equilibrium is going to look more like this. It's going to favor clear over to the right. But this guy, in contrast here, that's the weaker acid. So it's going to favor much more to the left. Okay. So it's going to favor it this way. So if we come back to our statement, good leaving groups are the conjugate bases of strong acids. So you see that this, compared to that, the hydroiodic acid is a much stronger acid than water. So when we look at the conjugate bases of these two, here's the conjugate base, and here's the conjugate base right there. Conjugate bases of strong acids are good leaving groups. This is the conjugate base of this guy right here. It's not a strong acid, so it's not a good leaving group. So a good rule of thumb is, in order for a leaving group to be a good leaving group, you want to look at their acid forms, and you want their pKa, okay, to be what? Less than 0. See if I'm writing that down right. Yeah, you typically want negative values for the acid component. And then if it has a negative pKa, then the conjugate base of that acid is going to be a good leaving group. So if we come back to our example here, which reaction will occur between this molecule and this molecule, you would say, hey, hydroxide is not a good leaving group, so that reaction cannot occur. But iodine right there, that is a good leaving group, so the substitution reaction can occur. And I used hydroxide as an example because just put that in your mind right now. Hydroxides, this group right here, hydroxides are not good leaving groups. Got it? Write that down. Not good leaving groups. Let's consider this reaction right here. We can treat it with any nucleophile. Okay. Mechanistically, we take the lone pair, the electrons on the nucleophile, and we take it and attack the electron poor carbon, and then break the carbon halogen bond. And that's going to give us this. That would have to be a X. Right? So what words would you use to describe what's happening here? You would say, hey, this is a substitution reaction. That is correct. What else can we say about it? Well, what type of mechanism is it? Hopefully you all see that it is a SN2 mechanism. Compare this substitution reaction to this one that I'm going to draw now. All right, something like that. Look at this. So we have lone pairs on that guy, so I'm going to make that leave. And then I will have something that looks like this. you'll have a carbocation plus the halogen that just left. And then we'll do another step right here where we will now introduce the nucleophile. Like that. So when you look at this reaction in the bottom, what words could you use to describe what has happened? In this reaction here, is it an elimination or a substitution? Well, it is a substitution reaction because we are replacing or substituting this halogen with the nucleophile. So both reactions are a substitution, but you can clearly see the mechanism between the two are different. So this one on the bottom right here has a name, and that's called a SN1 mechanism. So both are substitution reactions, but the way they occur is different. And that is the beauty of mechanisms. So this name right here, SN2, what it's referring to is S stands for substitution. So you can see in the SN1 reaction, you still have an S because they are substitution reactions. Now the N subscript right here is telling us that it is nucleophilic. We have a nucleophile doing the attack. So substitution, nucleophilic. Now this 2 right here stands for bimolecular. 2 means bimolecular. Bimolecular, or the 2, is referring to that in this SN2 reaction, we have 2 molecules. We have the alkyl halide and the nucleophile reacting at the same time. And we call that a concerted reaction. And since we have 1, 2 bimolecular, so we put a 2 there, SN2. And that's telling us that this substitution reaction is happening in a concerted fashion. 2 molecules are coming together and reacting. Now, can you contrast what this 1 is going to stand for? And can you take a guess? So what does 1 equal? So the 1 stands for unimolecular. And in a unimolecular reaction, do you see these green arrows here? That is an elemental step. Remember me referring to, at the beginning of the video, the elemental steps? You can see for each elemental step, there's only 1 molecule involved. And so when we have an alkyl halide and the leaving group leaves in this manner, we call this a heterolysis step. So this elemental step right here, I'm showing you the mechanism. The leaving group just leaves and generates a carbocation. Right? Now, in this step right here, we call that a coordination step. You can see that the nucleophile is negatively charged, positively charged. There's going to be an attraction there. And they're coordinating with one another. So that's a coordination step. and then that forms our product. Okay, so this SN1, or this one part right here, is referring to this first part of the mechanism. It's only using one molecule in the first step. The second step, you can see it's using two molecules. We're not worried about that in this definition, okay? Substitution, or SN1, is referring to this right there. And we're going to learn more about why that's the case. But from this point on, we are going to focus our attention only on this concerted mechanism and learn more about that. So you may be asking, well, what do we call this SN1 right here? We could call this a stepwise. It is a stepwise mechanism because it uses one elemental step, then another elementary step. That's what I'm trying to say. Elementary step, and then another elementary step. Okay. So now let's delve into this concerted reaction, SN2. There's a lot to talk about, a lot to learn. So as many smart people were studying reactions and trying to learn the mechanisms of, before they knew what it was called, SN2 mechanisms, they had to figure it out. And one thing that they learned about this is if they took the alkyl halide and doubled its concentration, but kept the nucleophile concentration constant, what they noticed was that the rate of this reaction, or the speed at which this reaction occurs, doubled. And then they said, hey, well, what if we kept this, the alkyl halide concentration constant, and double the nucleophile concentration? And what they found was that the rate also doubled. And so for our SN2 mechanism, the rate was simply the alkyl halide concentration multiplied by the nucleophile's concentration. And going back to rate laws, you will see that when that's the case, when this doubles, the rate doubles, or when you double that and the rate doubles, we have a second order reaction. And this second order reaction helped, just understanding the kinetics here, helped the scientists figure out the mechanism. Okay. So based off of this observation that it was second order, led them to believe that this reaction had to happen in a concerted fashion, in one step. So this is just one bit of information to help us understand the mechanism. But it is also good to understand this and know this, that in an SN2 reaction, it is second order. So if you double one of these, it's going to double the rate. Another very important thing about SN2 reactions is the stereospecificity. What do I mean by that? Well, what if I took a molecule that looked like the alkyl halide that looked like this? Now, let's put an ethyl group there, and we will keep that as a methyl. Okay. Now, when you take a nucleophile, and let's use this one right here. Okay. We take this nucleophile. Before it even reacts, we can look at this carbon here and say, hey, there's 1, 2, 3, 4 different groups. So we know that is a stereocenter. Now, what is the configuration of that stereocenter? You will see that it has a R configuration. Now, when we do this SN2 reaction, when we do this SN2 reaction, we know that means it's going to be a substitution. So we're going to replace this bromine right here. Look at how it does it. It's very, very important to see this. Look, the wrong molecule. Look at how it does it. CH3 and our ethyl. Can you see what happened? We did a substitution reaction. Yes, we did that. And so what should be over here? There should be the bromide that's floating around, right? The leaving group. But what happened to that stereocenter? Is it still R? You will notice that it is not still R. It is an S configuration. So what has happened? We have inverted the stereocenter. Whenever you have an alkyl halide attached to a carbon that is a stereocenter, and you do a SN2 reaction, you are going to invert the stereocenter. If it starts as an R, it will go to an S, and vice versa. If it started with an S, it would be inverted to an R every single time. Now, the reason for this is the mechanism of the SN2, the way it approaches. Okay? So I'm going to show you two approaches and show you which one's the correct one. So the first approach that I'm going to show you, the first approach I'm going to show you is called backside attack. So we'll say backside attack. And backside attack means that when you look at the molecule, you find the alkyl halide. And the nucleophile is going to attack 180 degrees from it. So that means the alkyl halide has to approach from this backside. So where's the backside with respect to this bromine? It's over here. So this halide, or this nucleophile, has to come in and go all the way around and attack backside. And when it attacks backside, it's going to invert the stereocenter. What does not happen is front side attack. The nucleophile does not come in and attack from the front. You see how I'm approaching it from the front side of this bromine? And then it leaves. It does not do that. So I missed one arrow with the backside attack. When the nucleophile comes in and attacks backside, yes, the leaving group does have to leave. Okay. So we have two ways to attack this alkyl halide: backside attack and front side attack. Front side attack does not happen. Backside does. Now, why would you say front side attack? Why would that not work? So that's a good question, good thought. We need to clean this board so we can answer that. So if we take and look at front side attack first, let's look at it in the transition state. So the transition state would look something like this. There's our methyl group, which I'll put right there. Me can stand for our methyl. Okay. And then there's my ethyl group here. So if this happened to be front side attack, what's going to happen then? The bromine bond is going to start to break, right? At the same time that the nucleophile bond is starting to form. Now this is kind of weird because this guy's trying to come in and this guy's trying to come out at the same time. It's a concerted reaction. And so it's just going to get really, really crowded. They're going to like be getting in the way of one another. Like, hey, I'm coming. No, you're leaving. And it's just like a little chaos here. And another thing is that there are a lot of electrons here. Major electron clouds. Partially negative, fully negative, and they're just going to repel each other. It is an electronic argument that there's just too many electrons around here. It's not going to work. But when you contrast the transition state to a backside attack, the way it really happens, you will see something that looks like that. Now, since these groups are 180 degrees from one another, you can see that the sulfur-carbon bond is forming. At the same time, the carbon-bromine bond is breaking. They're far away from each other. No electron clouds are going to interfere. This guy's coming in at the same time that guy's leaving. It is just so much better. So that's one explanation as to why backside attack is the only way it occurs. A more sophisticated way is to look at molecular orbitals. And so I'm going to have to clean up this board and draw those molecular orbitals so you can see what's going on. Okay, molecular orbital theory here. What we have is I changed the molecule a little bit on the alkyl halide. I replaced the ethyl group and the methyl group with hydrogens just to make the drawing easier. Okay. But even if I replaced these back with the ethyl and the methyl group, the principle would still be the same. So why do we not have front-side attack? Well, in MO theory, we realized that the whole molecule, okay, is a molecular orbital. And you see in green here, we have our methyl bromide here. Here's our carbon, there's our bromine. So this in green matches this. Now what you see in blue and pink right here is the LUMO of the alkyl halide. And chemistry is really simple when we say it. Chemistry is just the reaction of, or the interaction between the HOMO and the LUMO. That's all it is, okay? So if we take, so this right here, right there, is the LUMO. So if we take the HOMO of the nucleophile and try to attack from the front side, right there, to attack that molecular orbital, why is that a bad thing? Well, because I don't have my MO image 100% correct yet. Because right here, right down there, is a node. No electron density. So if we're proposing that this nucleophile is going to come and attack, that's impossible because there's a node right there. No electrons can exist right there, so you can't attack from the front. Because a node is a place where you'll never find electrons. So it's impossible. But if you look at backside attack, okay, you can see that, hey, look at this guy right here. Lots and lots of orbital overlap for the electrons in the HOMO to be placed into the LUMO. All right? So MO theory helps us to explain why backside attack is the only way to go. And then the, what's it called? The transition state drawing that I drew. Let's see, well, how much time do we have here? So let's just wrap this idea up by doing one example. So if I have a reaction that looks something like this. Okay, let's put chlorine. Okay. And I want to treat this alkyl halide with hydroxide. And I tell you from the beginning that this is going to be a SN2 mechanism. What is the product going to be? Now, you could memorize it, which I'm telling you right now is a horrible idea. Because you're going to get answer choices like this. If we call that A, we call that B. Okay. So you could see on an exam, you could have an answer choice of A, B, or A and B. And the problems can get even more complicated. We could have answer choices of A, B, C, and D. And then it could be, is it A and D? A and C, and it's just going to get very confusing if you're trying to memorize it. But if you do the mechanism, I told you it is an SN2, so just do the mechanism. And so you draw, it's like, hey, you're like SN2, concerted. It has to invert the stereocenter, because we know it goes by backside attack. So it can only be this product, because the mechanism says that. It can only attack backside attack. It's going to invert it. So the only answer is that. This is not going to be a mixture between A and B. The mechanism doesn't say that. Right? Very, very important to understand that the mechanism is going to help you predict the product. Now, if I told you this was an SN1 mechanism, then the answer is going to be different. But we don't want to talk about SN1s yet, because we are focusing our energy on SN2. Only one product, one answer. It has inverted the stereocenter. Okay, we will end there.